All right, we'll take a look at another problem here in section 4.5. We're going through a list of steps here in order to sketch a graph of a function. In the first three examples that I had shown you, they were kind of all algebra related, so let's take a look at a trig one next here. F of x equals sine x divided by 2 plus cosine x. All right, step one is the domain of f. Of course, I want to make sure I'm not dividing by 0. If you were to set the denominator equal to 0 and solve, 2 plus cosine x equals 0 means that cosine x would be equal to negative 2. Now the cosine curve we know oscillates between 1 and negative 1. So at no point will cosine x ever return negative 2, right? In other words, there's going to be no solutions to that equation, cosine x equal negative 2. So there's not going to be any x values that would return 0 in the denominator. The domain of f is all real numbers. Step 2 is to get the intercepts. Okay, when I set the function equal to 0 and solve, multiply both sides by the denominator. You got sine x equals 0. Well, that means that x would be 0, x would be pi, x would be 2 pi, 3 pi, right? So n times pi, where n is an integer. And to get the y-intercepts, if I let x be 0, if I plug 0 into the function, I'd have sine of 0 is 0, cosine of 0 is 1. Okay, 0 over 3 would be 0. So you're going to have infinitely many intercepts on this graph, and they would all be points of the form n pi 0, okay, where n is an integer. That would also include 0, 0, right, because 0 is an integer. Okay, step 3, the function is a symmetric function. It's symmetric to the origin because f of negative x and negative f of x are the same. If I were to plug in negative x, cosine of negative x is the same as cosine of x, right? The cosine function is an even function because it is symmetric to the y-axis. Sine of negative x is the same as negative sine of x. Okay, because the sine function is an example of an odd function. It is symmetric to the origin. So if I replace x with a negative x, and sine of negative x is the same as negative sine of x, and cosine of negative x is the same as cosine of x, well, the result of that would be like I would just put a negative in front of the function, right? These two expressions would be exactly the same thing, so the function is odd and therefore symmetric to the origin. Remember, symmetric to the origin just simply means any point that you plot x, y, negative x, negative y would also be on the graph. Also, f is going to be periodic, and the periodic factor would be 2 pi radians. Of course, the sine function and the cosine function are both periodic functions, where the periodic factor is 2 pi radians, and so that's another observation that we can make here in step 3. Okay, step 4, there's no infinite limits or limits at infinity to compute. I wouldn't have any infinite limits because I didn't have any numbers that were being thrown away as a result of division by 0. The domain is all real numbers. And I also don't have any infinite limits at infinity to compute because you see, if I were to set up a limit here, the limit as x approaches infinity of sine x over 2 plus cosine x, well, I know that both the sine curve and the cosine curve oscillate between 1 and negative 1. Now, the fact that both of these are combined into a function means that something that I'd want to notice early on here is that I'm still going to have some oscillating thing going on, okay? Well, if I have a curve that's oscillating between y values, it's not going to be approaching any one particular y value, okay? So that limit would not exist, is my point. There wouldn't be any asymptotes on the graph, so we can skip that. Okay, and now we're on to step 6. Step 6 is to get the first derivative and find the critical values. Well, I'm going to use the quotient rule. And okay, the bottom is 2 plus cosine x times the derivative of the top is cosine x minus the top, that's sine x, times the derivative of the bottom, that'd be negative sine x. And this is all over the denominator squared. Okay, and let's simplify that. You're going to have, when you distribute cosine x here, you're going to have 2 cosine x And then cosine squared x plus sine squared x, well, that's 1, right? That's my Pythagorean identity. So I'd go ahead and use that there and keep the denominator as is. And so now when I set f prime equal to 0 and solve, I'm going to multiply both sides by the denominator and get rid of the fractional form that I see there. 2 cosine x plus 1 equals 0. If you subtract 1 and divide by 2, then cosine x would be equal to negative 1/2. Okay, so if we draw a triangle where the adjacent side is negative 1 and the hypotenuse is 2, one angle that we would be describing is 2 pi over 3. Of course, both of these triangles would have to be in quadrants 2 or 3, right? If the adjacent side is a negative, you're going to the left of the center. So 2 pi over 3 would be the angle that we'd be describing there in quadrant 2. If you were to flip that triangle in quadrant 2 over into quadrant 3, that would not affect the adjacent side. It would still be a negative 1. The hypotenuse would still be 2 since you're talking about the radius of the circle. The opposite side will change, but we don't care about that in the case of cosine x, right? So cosine of 4 pi over 3 would also be negative 1/2. Okay, now there would be infinitely many critical values on the real number line here, okay? But I guess to avoid the additional calculations just being infinitely many numbers, like it was here, infinitely many intercepts, why don't we just continue the calculation on the interval 0 to 2 pi, and because we already know that the function is periodic with a periodic factor of 2 pi radians. So why don't we just take a look at what the curve would look like on the interval 0 to 2 pi, and then whatever we see there, we know it's going to repeat infinitely often in increments of 2 pi radians. So these would be the only two critical numbers then on the interval 0 to 2 pi. And now I'm on step 7. I can use the first derivative test. I've got my table set up here. Interval, number chosen, value of f prime, and then the conclusion. Again, I'm just focused on the interval 0 to 2 pi, and I've got my two critical numbers in order on that number line there. And that's going to force the table to split into 3 intervals for me. I can now choose my test values. So a number between 0 and 2 pi over 3 would be pi over 2. Of course, choose nice trig angles, ones that you can ideally do mental math here. If x is pi over 2, and you plug that into the derivative, cosine pi over 2 is 0. So you're going to have 1 divided by 2 squared is 4. Okay, and so that, cosine of 0 is, cosine of pi over 2 is 0. So this should actually be a 1/4, if you want to take note of that. Well, that's still a positive, right? So that's where I'm still going to be increasing on that part of the graph. If I were to let x be pi, next, plug that into the derivative. Cosine of pi is negative 1, times 2 is negative 2, plus 1 is negative 1. Okay, cosine of pi is negative 1. 1 squared is 1, right? So you're going to have negative 1 divided by 1 is negative 1. You're going to be decreasing on that part of the graph. And, sorry, I'm just going to change this real quick. I said that was 1/4 when you plug in pi over 2. I'll have to fix that in the notes there. Okay, and then if x is 3 pi over 2, cosine of 3 pi over 2 is 0, plus 1 is 1. Okay, so you get 1/4 there also. You're back increasing again. Okay, we go from increasing to decreasing. That's going to produce a local max at x equal 2 pi over 3. You're going from decreasing to increasing. That means you'll produce a local min at 4 pi over 3. If x is 2 pi over 3 and you plug that into the function, sine of 2 pi over 3 would be root 3 over 2. And cosine of 2 pi over 3, well, that's going to be negative 1/2, right, since that was a solution to this equation. And 2 minus 1/2 would be 3/2. So you've got root 3 over 2 divided by 3/2. When you flip the 3/2, the 2's would cancel, and that would leave you with root 3 over 3. Okay, that'd be the exact output. Root 3 over 3 is roughly 0.58, so I'll know kind of where to position that point there when I go to draw the picture. And then we got a local min at x equal 4 pi over 3. So let me state the local min as a point. When x is 4 pi over 3, sine of 4 pi over 3 would be negative root 3 over 2. Cosine of 4 pi over 3 is negative 1/2, since that was a solution to this equation here, producing a critical number. And, okay, so 2 minus 1/2 is 3/2. You're looking at negative root 3 over 2 divided by 3/2. When you flip the denominator, the 2's would cancel, and that would leave you with negative root 3 over 3. Okay, and now let's go to step 8. We'll calculate the second derivative. The second derivative is going to be a quotient rule, and within the quotient rule, you'll need the chain rule. And by the way, I had mentioned this I believe towards the end of the last chapter. I hope that you see that at this point they want you to be good at derivatives, okay? Like they want you to know what you're doing in the calculation. We've got a quotient rule, we've also got a chain rule, right? So that's why the practice was so important there in the last chapter. Hopefully you got that practice in. And because taking a derivative now is one out of several things that we're doing here in these problems, okay? And if we mess up the derivative calculation, like that's no good. So all right, when I use the quotient rule here, I have the bottom, which is 2 plus cosine x squared times the derivative of the top, that's negative 2 sine x, minus the top, 2 cosine x plus 1, times the derivative of the bottom, that's a chain rule. You're going to bring the power down of 2 times 2 plus cosine x to the first times the derivative of 2 plus cosine x, that's negative sine x. I'll go ahead and stick the negative sine x between these two parts here. And this is all over the denominator squared. Okay, and so now I want to simplify. To simplify, here's a 2 plus cosine x that is in common to these two groups. Let me go ahead and factor that out and cancel it with one of the 4 terms that I see in the denominator there. Okay, so I'm going to have a 2 plus cosine x cubed now in the denominator after I have pulled that out and canceled. Negative 2 sine x is also in common to these two groups, so let me go ahead and factor that out. So I've stuck this negative 2 sine x right out in front. Now, what's left over here from this? Well, we still got a 2 plus cosine x, and over here we've got a minus the quantity 2 cosine x plus 1. Okay, so 2 minus 1 is 1, and then cosine x minus 2 cosine x, that would be negative cosine x. So after you've factored out negative 2 sine x times 2 plus cosine x and then cancel the 2 plus cosine x with one of the 4 in the denominator, here's what you're left over with then in the numerator once you simplify that leftover. All right, let's set that equal to 0, and I'll multiply both sides by the denominator. That way I get rid of the fraction, and I can set these two factors equal to 0. Negative 2 sine x equals 0 means that sine x equals 0, so x would be 0, pi, 2 pi, 3 pi, negative pi, right? Increments of pi, although if I'm only focused on the interval 0 to 2 pi, here would be those 3 numbers. And if I set negative cosine x plus 1 equals 0, subtract 1 and then divide by negative 1, I'm looking at cosine x equal 1. Well, cosine of x is 1 when x is 0 and 2 pi and 4 pi and 6 pi. Well, I've already got 0 and 2 pi listed, right? Again, I'm only focused on when x is between 0 and 2 pi. So these would be the numbers that I'm going to work with next when I set up the table to use the concavity test. And again, I'm just on the interval 0 to 2 pi here. So really just that one number then, pi, is going to split this interval into 2 intervals. And I'll select my test values and find the value of f double prime here. So if in the first interval, if I were to let x be pi over 2, plug that into f double prime, cosine pi over 2 is 0. Sine of pi over 2 is 1. Okay, so you're going to have negative 2 times 1 is negative 2, divided by 2 cubed is 8. Negative 2 divided by 8 is negative 1/4. Here's another one. Okay, so if I select a number between pi and 2 pi, like if x is 3 pi over 2, plug that in. Cosine of 3 pi over 2 is 0. Sine of 3 pi over 2 is negative 1. Negative 2 times negative 1 is 2, times 1 is 2, divided by 8. 2 over 8 is 1/4. So we're concave up. All right, we switch concavity once at x equal pi. So when x is pi, well, that's going to be one of our intercepts, right? Sine of pi is 0. Cosine of pi is negative 1. 0 over 1 is 0. So, okay, pi is 0, you're going to have an inflection point. Now, if I'm only on the interval 0 to 2 pi, and by the way, just by the nature of the points that came up here with the local extreme, I decided to use a scale that went in increments of pi over 3 on the x-axis. We'll go between 1 and negative 1 on the y-axis. So just kind of running through the information again, and we'll just look at what we have on the interval 0 to 2 pi. We know that it's going to repeat in increments of 2 pi radians. Domain is all real numbers. Okay, we're going to have infinitely many intercepts here in 0, 0, pi 0, 2 pi 0, 3 pi 0, right? Negative pi 0. Okay, we're symmetric to the origin, so any point that we plot, x, y, negative x, negative y is also going to be on the graph. Okay, and that can be helpful. We've already said that the function is periodic. There's no asymptotes. We've got a max at 2 pi over 3, root 3 over 3. Root 3 over 3 is roughly about 0.58. Okay, so here's 2 pi over 3, come up to a height of roughly 0.58. And then we've also got a local min at 4 pi over 3, and then negative 0.58 roughly. All right, so here's 4 pi over 3, negative 0.58 is down there. I'm concave down from 0 to pi, so tangent lines are all going to have to lie above the curve, and that helps me see that there's this local max there. And then I'm concave down on the interval 0 to 2 pi, so tangent lines are all going to be below the curve, and so I'm going to have a local min at this point. Okay, and what I see on the interval 0 to 2 pi is going to repeat infinitely often. Okay, so I would repeat this in the next section of 2 pi radians, also to the left, covering the entire real number line there.